Now, what I report is the effects of the solid obstacles cyclic of on flag acceleration and deflagration to dilation transition. I will expand it on the following 4 parts. At present, faster initiation is still the focus of research in the field of power pollution. How to update initiation with a small amount of energy has always been the focus of research. One operable way is deflagration to dilation transition. Solid obstacles are added to the straight channel. The special structure of the combustion chamber will bring better flame acceleration than the transition the straight channel. Change the combustion chamber structure. The addition of the solid obstacles with different shape and different blockage ratio will bring strong change in the flame acceleration. Then and efficiently promote the DDT process. The following is the related research on solid obstacles. It is obvious from the figure that solid obstacles can significantly affect the flow states, increase the turbulence, and then effectively promote the flame acceleration. Combined with recent studies, it is found that flame acceleration and DDT process can be efficiently promoted by using a certain high blockage ratio and a certain distribution pattern in the uniform concentration feed. At present, there are more researches on the obstacle ratio involved in the obstacle shape structure, but the research on the obstacles cycles is efficiency. Therefore, it is very necessary to study the influence of the obstacles cycles on flame acceleration and DDT in this paper. In terms of numerical simulation and verification, in order to better simulate the flame acceleration process, we use a modified DDT form solver based on the OpenFOAM platform to solve the flame acceleration process. In addition, to reduce the numerical dissipation, we adopted the HLCLM. Previous study have shown that the increase of the number of obstacles can efficiently promote the flame acceleration and DDT process. But too many obstacles will reduce the promotion effect. The more uniform the concentration of the flow fluid, the better the initiation effect. Therefore, we designed the calculation L of the figure and arrange 4 groups. In terms of numerical verification, by comparing the flame possession change curve with time and the flame velocity and the position change curve, it is found that with the degrees of grid size, the 0.5 millimeter and 0.25 millimeter grid L is good agreement with the example and the numerical simulation of others. At the same time, considering the calculation accuracy and the computing resources, we use the 0.5 millimeter grid for simulation. The result and the discussion L are as follows. We designed 4 groups of case according to different thickness of obstacles, as shown in the figure. Several conditions are set for the thickness of obstacles, thin, general, thick, and extremely thick. the thickness of of solid obstacles from case 1 to case 4 is 5, 10, 13, and 90 millimeters. The initial flay development is similar, but it can be compared that the flay speed is fastest at 10 millimeter, and 5 millimeter is slowest. According to the design density gradient, it can be seen that the thickness of obstacles will affect the nearby fluid state. As a whole, the flay acceleration is dominated by the vortex formed behind the obstacles when the obstacle is seen. The real vortex also exists in the thicker obstacles, but the suction effect caused by the narrow channel formed by them plays a dominant role in the early stage of the flay development. Comparative analysis show that the overall flay flow velocity is weak at this time, and the suction effect formed by the velocity behind the obstacle is not as influential as the suction effect formed by the narrow channel on the flay development. When 10 millimeter is used, not only the suction effect of in order to further analyze the influence of obstacle thickness on flay acceleration, the flay velocity develops after the flay pass through the first obstacles. Before the flay reaches the second obstacle, the leading shock wave is significantly different. Use the action of obstacles with different thickness. When the thickness is 5 and 10 millimeter, the intensity of the reflected shock wave and the transmission shock wave behind the obstacle is greater, which will act on the flay surface faster, better accelerated the flow fluid behind the flay, and have a strong effect on the distribution of the flow fluid behind the flay, and have a better preheating effect on the uncombustible gas behind the flay, which is more conductive to accelerated development of flay. However, when the obstacle is too thick, the rear reflection shock is unstable, which is not conductive to the flay acceleration. Quantitative analysis of the flay acceleration process also shows when the flay interact with the obstacles, the flay acceleration effect is best when the obstacle thickness is 10 millimeter, followed by the 13 millimeter, 5 millimeter, and finally 19 millimeter. This is because when the flay start to interact with the obstacles, the effect of turbulence and vortex on the flay acceleration is increased compared to suction effect caused by the thicker channel. From the quantitative analysis, it can be seen that when the flay pass through the accelerated development of the first two obstacles, the initiation occurs near the third obstacles, combined with the initiation temperature and pressure cloud map. When the thickness of the obstacles is 5 millimeter, dilation 1 caused by the interaction between the flay surface and the reflected shock wave from the bottom wall. Dilation 2 caused by the interaction interaction of multiply compression waves in front and the flake surface. When the thickness of the obstacles is 10 mm, the flake is initiated behind the high pressure point. At this point, dilation caused by the interaction of the flake surface and the reflected shock wave from the bottom wall. Initiation time is the same when the thickness of the obstacle is 13 and 19 mm. Dilation caused by the interaction between the flake surface and the reflected shock wave reflected from the obstacles. And come by the case 2. Temperature and pressure distribution curve over time. It is found the small temperature gradient still successfully initiates the explosion. The detonation in this paper is consistent with Lieberman's flake acceleration model and the similar swatch mechanism. Finally, combined with the quantitative analysis of the initiation time and distance of 4 cases, it is found that with the increase of the thickness of the obstacles, the initiation distance will increase to a certain extent. However, the initiation time is not monotonous. When the thickness of the obstacle is 10 mm, the initiation when the thickness of the obstacle is 10 mm, the initiation time is shortest. Combined with the study of M on the initiation distance of smooth tube and obstacles feed tube on the basis of the obstacles blockage ratio, we added the influence of obstacles thickness on the initiation distance of tube with obstacles. And the fitting curve shown in the red dash line. In addition, the DDT run-up distance of obstacles feed tube formula is modified according to the influence of obstacles thickness, and shown in the red dash box. Combined with the above exercise and the research, the results as follows, like this. Thank you for your attention.